Hi everybody, my name is Anna Neuweiler. I'm a PhD student of the University of Potsdam, and today I'm going to present you what our group has been working on in the last year using our resources on SuperMUC-NG. We obtained a total of 44.1 million CPU hours for the last 2 years for our project of analyzing and interpreting compact binary mergers. So our group focuses on the study of compact objects such as black holes and neutron stars, and in that sense we are as well working on theoretical models to accurately describe those merging systems, but also developed a framework to be able to compare our models with observational data. For a better understanding of the dimensions I'm going to talk about on the next couple of slides, I generally like to compare the size of the neutron star to an average city. So I have here a map of Munich, and we can now plot the area a neutron star would cover in this map. It's roughly 20 kilometers, but the mass of the neutron star is about the mass of our sun. So we have a huge mass compressed to a small area, which is why the density inside the neutron star is incredibly high, and it reaches several times the density of an atomic nuclei. And we are simply not able to reproduce these conditions on Earth, which is why if we want to study matter under these conditions, we really have to study neutron stars. And this we can do by studying the merger of two neutron stars, or also the merger of a neutron star with a black hole. As a teaser, I'm going to start with a small movie of one of our simulations. So you see here two neutron stars that are orbiting each other, and while they do that, they emit gravitational waves, here displayed in yellow. In the bottom panel, you see the gravitational wave signal that is also observable by our detectors on Earth. And so while the neutron stars are inspiraling and emitting gravitational waves, they come closer and closer and finally merge. In this process, they also eject a lot of material, here displayed in purple, which has super high neutron densities. The remnant then forms some kind of accretion disk, and it also can collapse at a later point into a black hole. So we have a lot of different things that are happening here, and different things that we could observe. For once, we have the gravitational wave signal. Then by the ejected material, we have elements formed that radioactively decay and can trigger an electromagnetic transient that we call a kilonova. But we also can have a jet that is launched and that can trigger a gamma ray burst. So we have different signals that we can observe, and in fact in 2017 we were lucky enough to observe all those different things. So we observed the kilonova by telescopes on Earth and telescopes in space, but we also observed the gravitational wave signal by the gravitational wave detectors LIGO and Virgo. So I have here a picture of this L-shaped interferometer that can detect gravitational waves. We call this event GW170817 because it happened at the 17th of August 2017. And we also observed a gamma ray burst by the two gamma ray detectors in space, Fermi and Integral. So having all those different kind of signals from one source enabled us invaluable insight into those systems and several studies. So for once we could study, learn more about the expansion rate of our universe. We could study matter at supernuclear densities and also learn more about the formation of heavy elements, because most elements heavier than iron require for the formation super high neutron densities that are provided in the ejected material of this merger. So currently we think most of these elements have been formed in a neutron star merger. Okay, so for our studies, as I said in the beginning, we actually require accurate models, which is why the first part of my talk focuses on how we can perform simulations of compact binaries. Then in the second part of my talk, I'm explaining how we can then compare those models with observational data. We call that multi-messenger studies because we have different signals. We call them messengers, and yeah, so our multi-messenger studies. And in the end, I'm going to summarize our main results that we could obtain with our allocation on SuperMUC. Our simulations are based on general relativity, which means we have to solve Einstein's field equations. So here we have on the left-hand side the Einstein field tensor, which tells us about the state of the spacetime, and on the right-hand side we have the energy momentum tensor, which tells us about the state of the matter inside the spacetime. So in principle we have spacetime tells matter how to move, and matter tells spacetime how to curve. To solve the equations, there exist several approaches, also analytical ones. For instance, if we have low velocities, this is applicable, for instance, if we have a binary system where the objects are still very far away and velocities are low, then we can use Newtonian approximations. Similarly, for high mass ratios, so if we have a huge black hole and a small tiny one, we can use perturbation theory to solve the equations. However, if we have a system consisting of similar masses and the system is just about to merge and we have high velocities, those approximations are no longer valid and we really have to solve the field equations, which is only doable numerically. So looking back at the equations, having a 4-dimensional spacetime is generally very elegant, but we have here 16 nonlinear coupled differential equations, so it's rather complicated, and we somehow have to perform an evolution of the gravitational field in time, so we have to decompose them using a 3+1 decomposition. Doing that, the system of equation rather looked like this, so a bit more complicated. And for the evolution of one grid point for one time step, we have to perform 5,000 operations. Having a grid consisting of 100 points in each direction and performing the evolution for several time steps. So this is why our simulations are only feasible on high-performance computer facilities, and we really rely on our resources on SuperMUC here. Our group uses the BAM code, which is the state-of-the-art numerical relativity code. And BAM uses the methods of line approach to evolve the gravitational field in time and uses finite difference stencils to compute spatial derivatives. In our simulations, we have different things that we want to resolve. For instance, we have to resolve the strong field regions where we have steep gravitational fields, which is in the order of a few hundreds of meters, but we also have to resolve the far distances to extract some physical information such as gravitational waves, which we have to extract at distances of a few hundreds of kilometers. So, therefore, we use adaptive mesh refinement technique, where we have a grid consisting of several refinement levels. Basically, we have nested boxes where we have one coarse box with a coarse resolution and inside one with a finer resolution and so on. And the resolution always increases by a factor of 2. To save some computational resources, we apply for the time stepping the Berger-Oliger scheme. So simply because the smaller, finer box has to perform a smaller time step, the bigger one larger time step, so the smaller refinement level just performs a substep in between. And in that way we can save some computational time. For the parallelization, we use an hybrid OpenMP-MPI strategy. So simply, if we look at our grid, we can split the grid in the different boxes for the MPI processors. So here we have 4 processors, and in each regime, or for each box, we use OpenMP parallelization strategies. Of course, we did a scaling test for BAM on SuperMUC. So here we performed representative simulations using a grid consisting of 8 refinement levels. We did the simulation for 3 different resolutions and setups. Here for the lowest resolution, we used a grid consisting of 96 points in each direction for each refinement level, and for the highest resolution we had 192 points in each direction. And we see in the plot that for all the resolution, the scaling actually looks very linear, up to a few thousand, of course. And yeah, so here we used for the parallelization for each node 6 MPI processors, and for each MPI process 8 OpenMP threads. To show some results, I selected some highlights of our studies of the last year. So for example, we implemented the possibility to evolve dark matter inside the neutron stars. So here we included different percentages inside the core of the neutron star and analyzed how the gravitational wave signal is influenced. And what we observed was that the merger times actually shifted for later times for higher percentages of dark matter inside the core, and also the remnant lifetime, so the collapse into the black hole, is influenced by the different percentages of dark matter inside the neutron star. We also incorporated the possibility to implement more realistic microphysics because we want to use a better description of the neutron star's interior using models based on nuclear theory. And in that way, we can actually make more realistic evolutions for the ejected material after the merger. And last but not least, a very recent study that we are just about to submit to a journal is a study of a simulation for a neutron star merging with a subsolar mass black hole. I have also here a short video. So the black hole has here a mass of 0.5 times the mass of our Sun, and therefore the system is very outside the regime for typical gravitational wave models. And we used the simulations to compare it with those models and also with fitting formulas for the ejected material and remnant properties. And we saw that those models are actually not able to accurately predict what we observed in our simulations. And for that reason, the study showed that here still further development work is needed actually. The question is now, how can we compare our theoretical models based on our numerical simulations with actual observational data? So for that purpose, we developed the so-called NMMA framework. NMMA stands here for nuclear physics and multi-messenger astrophysics. And it allows us the simultaneous analysis of gravitational wave signal, kilonova light curve, gamma ray burst, all coming from the same source. And here we use Bayesian statistics to cross-correlate our observational data with our theoretical models and extract actual physical information about the source parameters. Here we use an MPI parallelization using a head-worker model. And here the most expensive part is to estimate the likelihood function, simply because we have a huge parameter space up to 80 different parameters. I simplified it here on 2 parameters and sketched here a likelihood function. So basically what we do is we randomly select life points in the parameter space and compute here the likelihood for these life points. Then we select the life point with the lowest likelihood and start here performing random walks in all directions. On all walks, we then select randomly another life point, where we then compare the likelihood function with the previous life point. If this one is better, we select this one as next life point, and then also look for the other random walk. If this one is better than the next worst likelihood of the life point, we select this one then also instead. And in that way, we improve our coverage of the parameter space to represent the likelihood function. So yeah, for this representation, we basically used 5 MPI processors. So one is the head that compares the likelihood of the life points, and the other ones, the other 4, they start the random walks and send the likelihood of the life point back to the head to be able to compare the likelihoods. For this parallelization strategy, however, the scaling won't be perfect, simply because it will also always depend on the number of life points that are chosen. We therefore show in the scaling plot here also the theoretical scaling for both curves. So here the yellow curve represents an analysis for gravitational wave and kilonova light curve, and the green curve represents the analysis of gravitational wave, kilonova, and gamma ray burst. Using this framework, we performed a study to learn more about the inside of the neutron star. So we started here with a set of equations of state based on current general effective field theory. So each equation of state gives us a mass ratios relationship, and so basically each line here is one equation of state. And in that way, it tells us more about what is happening inside the neutron star. The bottom panel here shows us the probability distribution function for the neutron star to have which radius. Basically, we see the radius is roughly between 11 and 12 kilometers. Okay, now we want to set tighter constraints by including more and more information. For once, we include information we obtained from observations for the upper mass of the neutron star. And we also included information we obtained from the NICER satellite. That one measures data from pulsars and can compute the mass and radius of a pulsar. And also we included information from the event 2017, from the gravitational wave event and from the kilonova light curve, and also the gravitational wave event 1904-25, where we didn't measure a kilonova counterpart. So including all of these information set tighter and tighter constraint to the equation of state that can then be translated in constraints for the radius of the neutron star. In total, our allocation allowed us to publish 14 papers and 2 preprints in the last 2 years, and we still have roughly 30 million CPU hours left until the end of this year to finish ongoing studies. I have here a small collage of all of our publications, and yeah, with this I would like to end this talk and thank you all for your attention.